This is part 2 of my lecture on comparing standard deviations, and I'm going to be talking about a single sample test. The single sample test is the chi-squared variance test. It's used to compare the standard deviation, or equivalently the variance, of a sample and a population. And it's used to test whether the sample could have come from a population with this known standard deviation. It's a parametric test, so the data must be quantitative, that is, they must be numbers that we can calculate with, and it should be normally distributed. Let's take the population to have a known standard deviation, which we'll denote by SP. We don't need to know the mean of the population. This calculation only looks at the standard deviation. It doesn't matter what the mean is. But we take a sample of NS measurements, and it's got a standard deviation of SS. Then the appropriate test statistic that we're going to calculate is called chi-squared. And chi-squared is NS times SS squared divided by SP squared. That is NS, the number in the sample, multiplied by the sample variance divided by the population variance, because SS squared, the sample standard deviation squared, is the same thing as the sample variance, and SP squared is the same thing as the population variance. To interpret this result, we have chi-squared is NS times SS squared over SP squared, and the null hypothesis would be that the sample has got the same standard deviation as the population. The width of both distributions is the same. That means that SS, the sample standard deviation, is equal to SP, the population standard deviation. So in this equation for chi-squared, SS and SP would cancel out, and we'd have chi-squared equals NS. So the expected value of chi-squared, if the null hypothesis is true, is round about NS. So we can calculate chi-squared and test it against the chi-squared distribution to see whether it's equal to NS. The chi-squared distribution needs to know the number of degrees of freedom, which as usual is the number in the sample minus 1. Note that this version of the chi-squared test can be one-sided or two-sided. When we looked at chi-squared before for a non-parametric test for comparing means of distributions, we said that version of chi-squared could only ever be a two-sided test. But here it can be one-sided or two-sided because the sample standard deviation may be greater than the population standard deviation, or it may be smaller than the population standard deviation. So SS may be greater or smaller than SP. We do have a direction to it. One complication of this is that the chi-squared distribution is not symmetric. So we have to take care in interpreting a two-sided result because it's not the same at the right-hand side and the left-hand side. Here's an example of the chi-squared distribution for 5 degrees of freedom. The shape and the mean of the distribution changes with the number of degrees of freedom. But here for 5 degrees of freedom you can see that because the chi-squared distribution can't go negative, it's cropped a bit more at the left hand end where it can't go below 0, with a longer tail at the right hand end. So I've shown here in purple the probability of getting a larger value, the right hand tail of the distribution, and in blue the probability of getting a smaller value at the left hand side of the distribution. Suppose, therefore, that we're looking for a one-tailed test at the 5% significance level. We want to know what is the probability of getting a value in the right-hand tail here, which only occurs with a 5% probability. So if we look in the purple values, a p-value of 0.05 corresponds to a critical chi-squared of 11.1. So any value above 11.1 is in the right-hand tail of the distribution, which only occurs with a 5% probability. So If our alternative hypothesis is that the sample has a larger standard deviation, then we need chi-squared is more than 11.1 in order to satisfy that hypothesis. On the other hand, if the alternative hypothesis is that the sample has a smaller standard deviation, then we need chi-squared less than a value in the left-hand tail, and 0.05 in the left-hand tail corresponds to a critical chi-squared of 1.2. So we would need chi-squared less than 1.2 in order to satisfy that alternative hypothesis and disprove the null hypothesis. On the other hand, if we're doing a two-tailed test, if we want a 5% significance level for a two-tailed test, we need 2.5% in each tail to get a total of 5%. So in the right-hand tail, if we look at a value of 0.025, we see that chi-squared is 12.8, so we'd need a value more than 12.8 to get in that tail. And in the left-hand tail, for p equals 0.025, we see that the critical value of chi-squared is 0.8, so we'd need a value of less than 0.8. So for a significant result for a two-tailed test at the 5% level, we need chi-squared less than 0.8 or greater than 12.8 to get into one of those tails. Let's take an example based on radioactive counts. The question that we might be asking ourselves is, if we take 10 repeat measurements of the same source, is the variation in counts what we expect due to random statistics? Here we've got a small radioactive source that we're putting into a well-typed scintillation counter, and it's inside a lead shield to keep away background. And we're going to set the counter going to see how many counts we can detect in a fixed time of, say, 30 seconds. Here the counter's clicking away happily. We've just got to wait for the 30 seconds. There, the 30 seconds are up now, and we've got 509 counts. So there we saw that in 30 seconds we obtained 509 counts. If we repeat that 30-second count again, we're not likely to get exactly the same number next time. Next time I did it, we got 495. And then the following time, 518. Then 531, 526, 482, 516, 478, 535 and 480. So those counts vary somewhat about the mean, as you might expect due to radioactive counts, and we want to say, is this variation what we expect? So the experimental hypothesis might be that the variation in counts does not follow the Poisson statistics, and the null hypothesis is that the variation in counts is consistent with Poisson statistics. Note that's a two-tailed test because it could go in either direction. The statistical test requires the fact that the data are quantitative, and we can assume the population is normally distributed. We know that they should follow a Poisson distribution, but for reasonable sized numbers the Poisson distribution is approximately normal, so we can use that fact that it's normally distributed. And in fact the standard deviation is known, because the standard deviation of a Poisson distribution is just the square root of the mean. So here we can use the chi-squared variance test to compare our sample standard deviation with the expected population standard deviation. So here are the sample data. The first count was 509, the next 495, 518 and so on. If we add up all those 10 counts, we get a total of 5,070. There were 10 of them, so 5,070 divided by 10 gives a mean of 507. That's the mean count. We want to calculate the standard deviation for this test, so we have to calculate the deviation from the mean. If you remember to calculate the standard deviation, the first thing we do to calculate the deviation from the mean is take the mean of 507 away from each of those measurements and then square it. So 509 minus 507 is 2. 2 squared is 4. 495 minus 507 is minus 12, and minus 12 squared is 144. Remember, when you square a negative number, it becomes positive. 518 minus 507 is 11, and 11 squared is 121, and so on for all 10 measurements. If we add up all the squared deviations, 4 plus 144 plus 121 and so on, gives a total of 4,266. That's the total squared deviation. The variance is defined as the mean squared deviation, so we divide 4,266 by 10, and that gives 427. The mean squared deviation is what's known as the variance, and the standard deviation is the square root of that. So the square root of 427 is 20.7. So now we're in a position to calculate chi-squared. Remember, chi-squared is ns times the sample variance divided by the population variance. Now in this example, ns is 10, and the sample variance we just calculated to be 427. We just need to know the population variance. Well, if Poisson statistics apply, then we know that the expected population variance is equal to the population mean. That's what happens with a Poisson distribution. It's another way of saying that the standard deviation is the square root of the mean. The variance is equal to the mean. Now, we don't know the population mean, but our best estimate of the population mean will be the sample mean of 507. So we can take 507 as being the population mean, and hence 507 is also the population variance because Poisson statistics apply. That means that chi-squared is ns of 10 multiplied by the sample variance 427 divided by the population variance 507, which comes to 8.4. The number of degrees of freedom is the number in the sample 10 minus 1, so that's 9 degrees of freedom. So we have chi-squared of 8.4 for 9 degrees of freedom. Here's a table of the chi-squared distribution. Remember, we're doing a two-tailed test, so for a 5% significance level we have to look at 2.5% in each tail. If we start with the left-hand tail, in blue we see here that a probability of getting a smaller value at the 2.5% level, p equals 0.025, for 9 degrees of freedom corresponds to a critical chi-squared of 2.7. And in the upper tail, a probability of a larger value with a p of 0.025 for 9 degrees of freedom corresponds to a critical value of 19. So we need chi-squared less than 2.7 or more than 19 for a significant result. So we've just seen there from the table that for 9 degrees of freedom for a two-tailed test at the 5% significance level, we're looking at 2.5% in each tail. So for p equals 0.025 in the lower tail, we need chi-squared to be less than 2.7, and for p equals 0.025 in the upper tail, we need chi-squared to be greater than 19. If you remember, our chi-squared was 8.4, which is between those two values. It's in the middle of the distribution. It's not less than 2.7. It's not more than 19, so we don't have a significant result. So we can't reject the null hypothesis. So in this case, we have to conclude that the variation in sample counts is consistent with the null hypothesis. That is, the counts are compatible with the expected Poisson distribution due to Poisson noise. Note, if you're going to use this to estimate Poisson noise, you have to take the square root of the mean of the total counts, not the counts per second or the counts per minute. Here I was taking the counts that we actually got in the 30 seconds that we acquired, rather than counts per second or counts per minute. So that's an example of how you can apply this statistical test to check that the variation in radioactive counts is exactly what you expect it ought to be. And that's the end of part 2 of this lecture.